This is the fourth thing. Oh, thank you. Who is recording this? Rico?
Rico, Bapak.
Okay, thank you, Rico. Today, we will continue our discussion about hydrogen atom. And I hope you guys can be patient before we really go to density functional theory. So we are going to go to the density functional theory, but be patient. Can you hear me, bro?
Yes, we can hear you.
Okay. All right. Before we go to the hydrogen atom, let us go back to what do we have so far. And this presentation also will be provided to you. I will save it into PDF and put it in our cyber campus. If you still have some problem with cyber campus, I will just give it to Dr. Mark, Dr. Lucia, and Dr. Vera. Remember so far that according to traditional chemists, they got a problem when explaining the resonance structure like ozone or benzene. I told you this story already. And not only about ozone and benzene, traditional chemistry also read a problem with conjugated bond. All molecules with alternated single and double bonds, alternated single and double bond, it is what we call conjugated system, do not follow the structures predicted by traditional chemistry. This is for one example. And the question is, are the double bond really there? It is here or over there, we don't know. According to traditional chemistry, if it is double bond, the bond length must be shorter than single bond. But experimental doesn't prove it. Experimental says something else. Then comes to my hero, not your hero, it is my hero, my father. He explained about the great idea from Linus Pauling. You can see here, pendulum A moves. Dr. Lucia, you can see the video?
Yes, I can see it.
Okay, thank you. You see? And now B is moving, while A is starting to silent. Look. A is going to be at rest. B is now moving. You see that? And now B is begin to slow. And A now gain momentum. You see that? B is going to be at rest. B akan diam. While A is moving forward, moving faster. And now you can see that now B is at rest, diam. What happened? Why? Well, anyway, the video stucks. Anyway, so what we let us see what is going on here. Wait. A and B are one system. We call it coupled together. So we cannot distinguish them. We cannot separate them. They are one big system. Consists of pendulum A and pendulum B. A, while it is moving, A transfers energy to B. And how we model it in classical physics, we use spring to transfer the energy. A is to rest while B is moving. So you see that before, right? You saw it that while first A is moving, B is at rest. And A now is begin to stop the motion, and now B is moving, and so on. Point two, this one is we call it internal affair because it is actually one big system. As the observer, external affair, we always say the system is always happen. In engineering physics, Itera, can you mute your microphone?
We don't join the microphone.
Okay, great. So what I just explained to you, what was the classical physics explaining resonance. A moves and then transfer energy to B, B moves while A at rest. While B is moving, B then transfer energy to A now is moving while B is at stop at rest. Resonance is the interdependence of position in a coupled system. Coupled system. I will fix it later, the grammar. So this is the definition of resonance. The interdependence of position in a coupled system, like a coupled pendulum. We can use the exact concept to hydrogen ion molecule, H2 plus. Hydrogen ionic molecule has two nucleus, A and B, A and B, A and B, and one electron. Of course, according to classical physics, classical chemistry, the electron only can orbit at one nucleus at a time. So the electron either orbiting nucleus A or it is orbiting nucleus B. It cannot orbiting both at the same time, cannot. So if we apply the resonance into hydrogen ionic molecule, what happens is first the electron this one, first orbits nucleus A, and then suddenly it moves to orbit nucleus B like this. And then go back to A, to the left side of the diagram, and then move to the right side of the diagram, and so on, exactly like what happened in coupled pendulum. First, A is moving, B is at rest. And then A transfer energy to B, B is moving, and A at rest. Electrons moves from one to another nucleus. So that's the same concept of resonance inside molecule. This concept is applied to the ozone structure. We now apply the same concept, the resonance concept, to the ozone structure. This is what chemists call mesomeric effect, if I remember correctly. You see that? Atom 3, 1, and 2, ozone, O, and O, but I put it 3, 1, and 2 to make it easy to call it. Electron, some electron, this couple electron from 3 move to this bond, while 2 electron from this bond move to oxygen 2. So that's what we got resonance, like this. First, it is like this. Then, at some point, it changes, the structure becomes like this. And then go back to the left, go back to the right, go back to the left, go back to the right, and so on. That's what exactly resonance is. But remember, in the measurements, there are 6.023 times 10 to the power of 23, the Avogadro number of ozone molecules, not only one molecule. So when we measure one time, we measure many molecules actually. So that's why we have the measurement result like this. The average plus minus standard deviation. And for the bond length, R1, the bond length between 3 and 1 is equal to R2 between 2 and 2, 1 and 2, and it is 1.272 Armstrong. They are identical, they are symmetric. If we apply the classical chemistry, R1, this one, should be 1.475 Armstrong. And R2, the double bond, is around 1.207 Armstrong. So this is how we explain the resonance structure of ozone. The electron can move, switch position, switch orbit or the orbital or the orbiting system to the nucleus A, move to the nucleus B, and so on and so on. To make it happen, the question now is, how does the electron move from one to another nucleus? So this is the case for hydrogen ionic molecule. This one, sometimes it goes this way, and another time it goes to the right side of the schematic. It is the same, exactly the same for ozone in the figure below, this one. So it is about electrons move from one nucleus to another nucleus. You got it right? If you go back to the the couple pendulum, I will fix the grammar. In couple pendulum, it is the spring that oscillates. Oscillation carries the energy. We call it resonance energy in the form of wave. While in hydrogen ionic molecule, it is the electron that must behave like wave to carry the energy of resonance. If it is not wave, it cannot move. So that's the bottom line. The point. The point is, we can move, electron can move from one nucleus to another nucleus if it behaves like wave. If it is not behave like wave, it cannot move. It is classical physics. It cannot move. Once it is there, it is there. Like for example, our solar system, we have Earth orbiting the sun, and then moon orbiting the Earth. It is not quantum system, so moon never orbiting the sun. It is always orbiting the Earth. But if it is quantum system, suddenly moon can orbit the sun, and we lose the moon. We don't know when to pray anymore, when it is Ramadan. Fortunately, our solar system is not quantum realm. If it is quantum realm, if it is quantum system, moon can jump to orbiting the sun. It is exactly like what happened in a hydrogen ionic molecule. So you can imagine this is Earth, this is sun, and this is the moon. And suddenly, you don't know why, you don't know when, you even don't know why the moon jumped to the sun. So that can happen if moon behaves like wave. How electron behave like wave? Now it comes to the quantum theory. It is possible to study electrons behave like wave when we study the particle using equation of motion for wave. So we must study electrons using wave equation of motion. So we flip it, right? Remember, right? That's quantum theory. If it is particle, study it with wave. If it is wave, study it using equation of motion of particle. This schematic is really important to understand quantum theory. And the mechanic, this is quantum theory. You flip it, you swap the equation of motion. This is quantum theory. The mathematics behind it, the mathematics to explain the mathematical formula to make equation of motion, we call it quantum mechanics. So quantum mechanics is about mathematics. Quantum theory is about idea. And classical mechanics is a special case of quantum mechanics. So it is like a Venn diagram. The big one is quantum mechanics, and the small one is quantum physics. Classical mechanics. And when we study particle using equation or wave equation of motion, one of the equation of motion that we can use is the Schrödinger equation, this one. And you don't have to be scared about this equation. It is called normal equation. You don't need to be scared about it. Why? Let us see. We have this equation. It is wave equation. Why? Because the solution is wave function. Wave function is always about time and position. Wave function has two variables. Always remember that. Wave function always has two variables, position and time, or time and position. Okay? It is for particle. Why? Because we have mass in the equation. The only object has mass in the universe is particle. Wave doesn't have mass. Wave has wavelength or frequency. So we have wave because the solution is wave function, this one, and we have mass to indicate we are talking about particle. And mathematically, we go to the mathematical domain. This equation can be split into two equations, time domain and spatial domain. When we split it into two domains, we have this equation. We call it time independent Schrödinger equation. Why? Because now time variable and spatial variable, space, split it into two separate systems. Above is for the function of time, and below is for function of position. And function of time is always like this. You don't need to change anything. It is always like this. So if you have this one, if you solve this, you got the wave function of the spatial domain. You times by this, you got the full wave function with variable of time and position. But for the wave function of spatial domain, you have to define what is the potential energy. The kinetic energy is always the same for all systems, but for the potential, it is unique for particular system, for each system. So potential describe the system. Now we look at the hydrogen atom. But I will give you like 1 minute to take a note. All right. Now look at the simplest case, hydrogen atom. And last week we know that there are two ways to model the hydrogen atom. Either we consider the proton and the proton and electron, we got two body problem, or we only consider electron, we got one body problem. These two methods are valid. In fact, Kasei Sensei, the supervisor for Dr. Mark in Osaka, he used two-body problem when solve hydrogen in his software Naniwa series. But anyway, for us, we will use one-body problem. Why? Because two-body problem, you can see the potential. There is a potential here which contain two positions. And the implication is the wave function also contains two particles which couple. So we have resonance here, and we cannot solve it using the common mathematics. So better for us to use one body problem. We remove proton. We only take the potential field of the proton. So we got this formula. Sorry, this is equation, the Schrodinger equation. Now the wave function we got here is only for electron. If we have two-body problem, the wave function is both for proton and electron. And it is difficult to solve. But here, since we only deal with one body problem, the C in the Schrodinger equation is the wave function of electron. While the potential, this and the potential energy of electron belong to electron. So everything here is belong to electron. Mass belongs to electron, potential energy belongs to electron, wave function belongs to electron, later on energy belongs to electron, and kinetic, this is kinetic, also belongs to electron. So everything belongs to electrons. So that's what we call one body problem. And the potential energy of electron due to the Coulomb potential field, we got this formula. I need to write it down because I need this later on to explain to you what is heart rate or dimension. And the unit is volt, like a battery. When you buy battery 1.5 volt, this means the potential, the Coulomb potential field. It generates by Q. Q is the proton, but we don't consider Q anymore. We only consider this one. Now, when you multiply by Q, capital Q, the electron, you got the potential energy. This is the potential energy of electron. And now the unit is joule because it is energy. This one, potential field. This one, potential energy. Different units. Now, the electron, so we have this equation now. Look. This is the general equation. Now, we consider the Coulombic potential only, this one. The electron only moving around certain area. That's what we call bound state. The electron cannot go anywhere, only at certain area. If the electron cannot go, it can move, but cannot go anywhere, we call it circular motion. The natural coordinate for circular motion is spherical coordinate. You got it? Okay. This is the spherical coordinate. We have radial and then theta and phi. Next. Now, the position we describe as r, theta, and phi, which means the wave function now is r. We can split it into radial wave function and azimuth wave function. Radial wave function and azimuth wave function. If we do that, we got the equation that the solution already exists long time ago. Mathematics already provided the answer. If using this kind of equation, or the radial function is the solution, or is Laguerre function, while y, the azimuth wave function, is spherical harmonics functions. So we got the solution already. We don't need to derive one by one. And you see that Laguerre function contain two new parameters, n and l. So please find in Wikipedia to find the difference between variable and parameters. So a function can have variable, also can have parameters. Please find the difference. While harmonic functions, the harmonic functions contain one parameter. L is the same with Laguerre, and the new parameter is M. And the parameters N, L, and M are pure mathematical needs. There is no physical meaning at this point. We got it from mathematics. And finally, we got the solution. The wave function of electron is radial times azimuth. And if you want to consider time, you can the variable of time, you can multiply by v, the previous one that I just showed it to you, exponential mean minus I e over h bar and times t. All right, now we radial wave function, we can plot it. This is logarithm function basically. So we have R10, the red color, this one. And then R20, green, green, this. And then R21 means N is equal to 2 and L is equal to 1, dash green, this one. And then R30, pink, this one. And finally R31, pink dash, this one. Dr. Lucia, can you see my cursor moving?
Yes, I can see it, Dr. Freddy.
I'm really sorry because I got my running nose doesn't. If you cannot hear my voice, please tell me. So we can plot it, and this plot already exists before Schrödinger equation born. I tell you again, this plot already exists before Schrödinger equation born. Now the question is, what do they mean? What do the single plot mean? What does it mean? To understand the meaning, then we have to go back to the quantum mechanics. The meaning of the wave function, we use Born statistical interpretation. It is one of many interpretations of quantum mechanics. Remember, when we use quantum theory, when we study particle using wave equation, or when we study wave using particle equation, we lose the common sense. The common sense or the sebab akibat. What is it in English? What is sebab akibat in English, Lucia? Sebab akibat.
Maybe cause and effect.
No. Bro. Sebab akibat in English.
Consequence, is it?
No. But there is a law in classical mechanics. In Indonesia, we call it hukum sebab akibat. Hukum sebab akibat. Hukum sebab akibat, in other words, is common sense. And that common sense disappears when you use quantum theory. Common sense exists because we study particle using particle equation, and we study wave using wave equation. That we have common sense. Causality laws. Causality. Find it in Google, read in Wikipedia if you don't trust me. Causality law exists because we study particle using particle equation, we study wave using wave equation. If we flip it, we study particle using wave equation, or we study wave using particle equation, we lose common sense. What does it mean? It means the dimension doesn't make sense anymore. The wave function that actually explained to us about the energy and so on in classical mechanics, in this case, we don't have that meaning anymore. The wave function does not have any meaning. The wave function of particle does not have any meaning. So we need to interpret it. In bahasa Indonesia, we need to takwil. So we have terjemah, tafsir, and takwil. Takwil means interpretation. It could be wrong, it could be correct. And Many people try to interpret quantum mechanics. One of them provided by Max Born from Germany, and he was one of the student of Niels Bohr. So we have Born, we have Bohr. Max Born was the student of Max Bohr. Wave function in this case does not have any physical meaning, but according to Max Born, if we square and if we take the absolute value and square it, because remember the wave function could be complex function, imaginary. It contains imaginary function. So to get rid of the imaginary function, we have to take the absolute value and square it. And this, after you do this, can be interpreted as the probability density function or PDF. When we talk about probability density function, we talk about statistics. So that's why we call it Born statistical interpretation. And believe me, you have to read the book or read the Wikipedia. The only person does not like this interpretation is the only person in the world does not like this interpretation is Schrödinger itself. He didn't agree with this interpretation. He make a new interpretation, Schrödinger interpretation, but no one use it. He was so sad, but I don't care. You have to read about Schrödinger, yeah? Really good story. Of course, this is not the only interpretation we have. We have Born interpretation, we have Schrödinger interpretation, we have many things I cannot explain to you at this time, but many. But we use Born statistical interpretation because why? Because in molecule, in atomic and molecule, it works perfectly. But when we use for other thing like cosmic rays in the sky, Born statistical interpretation doesn't work. So we need to use another interpretation. So according to Born statistical interpretation, remember Born statistical interpretation works perfectly in the world of atomic and molecule. So we don't need to use our other interpretation. If we integrate the probability density function of our volume between A and B, we call it probability of finding particle between A and B. So this is statistical knowledge. This is statistic branch of mathematics. So quantum mechanics is indeterministic. Yes, unfortunately, yes. Everything by chance. If we use statistical interpretation. So that's why perhaps you see this figure, famous figures between this is Niels Bohr and this is Albert Einstein. And you got the story, you know the story, how they debate so heat the debate, but they still friends. The idea they don't like their each idea, but they are really close friends. I really want to have this relationship with Dr. Mark, but I don't want it anymore. Okay, so what Einstein says about Max Born interpretation. So after the debate, Einstein cannot answer anymore because Born give very good argument. Finally, after the conference finished, they go home to each respective house, and Einstein wrote a letter to Max Born, and he said in the letter, the theory, I mean your interpretation produces a good deal, but hardly brings us closer to the secret of the All One. So this means God. I am at all events convinced that he, God, does not play dice. Because according to Marx's interpretation, everything happens by chance. Jadi kalau kita gunakan interpretasi statistik Born, wave function itu diterjemahkan sebagai amplitudo probabilitas. Amplitudo probabilitas kalau kita kuadratkan menjadi probability density function. Ini bahasa statistik. Karena kita sudah menggunakan probabilitas, kita bicara indeterministik. Indeterministik artinya kita tidak tahu apa yang akan terjadi di depan sampai kita melihatnya sendiri. Itu namanya apa? Indeterministik. Nah, two initial state, the exact initial state, dua kondisi yang sama dapat berakhir pada dua ujung yang berbeda. Jadi tidak mungkin atau boleh terjadi tidak sama. Itu namanya indeterministik. In other words, cara lain mengatakannya adalah semua fenomena yang terjadi di dalam atom dan molekul menurut kuantum mekanik terjadi karena kebetulan, Dr. Lucia. Jadi Dr. Lucia jangan terlalu percaya mekanika kuantum ya, karena kita percaya Tuhan. Kita pengikut Einstein. Nah, Dr. Lucia jangan lagi meriset pakai kuantum ya. Cari riset yang lain. Okay, guys. Okay, so now the left side of the figure is the radial wave function plot. Now we square it. We take the absolute value and we square it. We got the figure on the right side, this one. We call it PDF, probability density function for R10, R20, and R21. Now, we consider only the first one, the red one, PDF for R10. We have two in statistic. This is pure statistic terminologies. We have the most probable value, nilai yang sering muncul. And then we have the expectation value, nilai yang diharapkan atau rata-rata. Ini bahasa statistik. The most probable value pasti yang ada paling puncak. The expectation value adalah kita integralkan, cari nilai tengah yang luas kiri sama dengan luas kanan. Dr. Lucia, can you follow me?
Yes.
Yeah, for hydrogen, Dr. Lucia, for hydrogen, the most probable value is exactly 1. 1. And for the expectation value is 1.5. 1.5. I don't talk about the unit yet. Later on, we will talk about the unit. 1 and 1.5. Okay, the unit is Bohr. The time I will explain later. Now, we go back to the slide before. What do they mean? The answer is it does not mean anything unless we square it. And then we got the probability density function. And it is the same for the azimuth wave function. We got something like this: y00, y010, and y21. This is just an example. And we cannot, for the radial, it is 1 dimension. But for the azimuth, we have to plot it in 3 dimensions because azimuth contains phi and theta. It requires 3-dimensional coordinate. So we got like this. And still it doesn't mean anything until we square it. And long story short, using these two kind of wave function, we multiply them, radial and azimuth, and finally we got what we know already, hydrogen atomic orbital. We have 1s, 2px, 2py, 2pz, 3dxy, 3dxz, and so on. 1s is 100, 2p is 21m, so this using NLM notation, and d is 32m. But I have to warn you, this is not the same as m minus 2 minus 1. No, it is not like this. So matching up with the spectroscopy knowledge, NLM, or I will fix the grammar, or the quantum number. However, pure NLM are complex functions. Therefore, chemists use linear combination of NLM to match up with the spectroscopy notations. For example, 2px, this one, constructed by 1, 1 plus 1 minus 1, 1 minus 1. And for 2pz, 2py, 1, 1, sorry, this, yeah, 1, 1 plus 1. Oh, sorry, this must be 2. Yeah, 2. 2, 1 plus 1 minus 2. Okay, I repeat it again. 2px is the combination, the linear combination of 2, 1 plus 1. This is m. N, L, m. Minus 2, 1, minus 1. This is m equal to minus 1. This is 2.
Sorry, can you hear me? Oh, I think your image is blocking the equation. I can't see. You can't see. Yeah.
Oh my God. How dare
this-
you? Okay, I will move now here. You see now?
Yes, yes. Yes.
But I made a mistake, bro. It must be 2 here.
Okay.
You see? 2, 1 plus 1 minus 2, 1 minus 1. This is 2px. 2py is 2, 1 plus 1 plus 2, 1 minus 1. That's 2py. While 2pz is 2, 1, 0. Because 2, 1, 0 does not contain any imaginary function. So it is free from complex function. I will repeat it again. I go back to the previous slide. Okay. So the solution of Schrödinger equation, when we consider the potential comes from the Coulombic potential field, is two functions, Laguerre functions and spherical harmonic functions. Laguerre functions contain two parameters, M and L, while spherical harmonic functions contain another two parameters, L and M. L and M. This L is equal to that L. So we have three parameters. If we multiply R and Y, radial and azimuth, we have three parameters, M, L, and M. And these parameters are pure mathematical needs. At this moment, there is no physical meaning. Then we plot them, we plot the radial, we got this. And we plot the azimuth, we got this. We multiply them. We got orbital. We got orbital like this. And these orbitals is not the same with the previous one. This one, R alone and Y alone. R, Y. Now we multiply them together. Not only multiply, we project them. We make some linear combination to get rid of the complex function inside the orbitals. So that's why, for example, 2px comes from, look above my head, 2px comes from 2, 1 plus 1 minus to 1 minus 1. So that's why we have 2px, 2py, 2pz. If we don't do this, we cannot draw them in the figure because complex number. And for d orbital, we have 5 d m minus 2 minus 1, 0, plus 1, plus 2. But when we do combination, linear combination of these 5m, we can have 5 new orbital, or we can have 6 orbital for d. Depends on how we multiply them. The point is, we don't want complex function. We need to have all real functions. So that's why we have to twist the mathematical formula of the orbital. In the end, we have hydrogen atomic orbitals. And after we do this, we got exactly the same with what the spectroscopy people already had long time ago. 2, 1s, 2p, 3d, and so on. It is spectroscopy notations. They have it already. But using quantum, we can match them. We can make parallel between the NLM parameters and SPDF spectroscopy notations. So that's why we call it NLM as a quantum numbers. Now it has physical meaning. Before that, we don't have physical meaning for NLM. After we twist a little bit, now we have the physical meaning. I hope I make it clear now. Now, the question is, what does an orbital mean? What does the orbital mean? According to the traditional chemists, orbitals are like room. We usually use this analogy like a room. Each room may occupy by maximum 2 electrons. Right, Dr. Mark? Where are you, Dr. Mark? So this is what usually we explain to students, right? About what is orbital, right? We use this analogy. However, this analogy is not correct because you cannot contain electron in room. It behaves like wave, remember? It behaves like wave. You cannot contain wave in a room. And furthermore, who are you to tell what electron can do? Remember, this is indeterministic. So the analogy used by the traditional chemist has a fundamental flaw that electron cannot contained by inside one room, and plus, who are you to tell what electron must do? However, rightly guided chemists like Dr. Mark will explain to you that orbitals are the mathematical descriptions of wave-like behavior of electron. Remember that? Orbitals are the mathematical descriptions of wave-like behavior of electron. And we don't talk about spin now. We just ignore spin for this time. At this moment, we don't talk about spin. We don't need spin. All right, let's move. This is also important. Atomic unit, length in Bohr radius. We have this equation, Schrödinger equation. This is kinetic, this is potential, and this is wave function. And we know E is energy, but I don't talk about energy at this moment. Now, we change R becomes A0 times another R. I call it R ring because there is a ring above R. R ring. Because we change R becomes A0 times R ring, Laplacian operator becomes like this. Oh, must be square here. Dr. Lucia, I made a lot of mistake. Please take a note. Page 32 must be square here. And 1 over R becomes like this. Okay. Now we substitute point number 2 to point number 1. Now we have like this. You see, this times A0 square from this one. Dr. Lucia, can you see it?
Yes, I can see it.
And now 1 over R becomes 1 over R ring, and there is A0 in the left. Dr. Lucia?
Yes.
Since we already changed everything in the left side, E must also change to another E. They are not the same anymore. Dr. Lucia?
Okay.
Mark, Dr. Lucia just graduated yesterday, Mark. You must congratulate her.
Sorry, come again.
Now, after we have point 3, we must select A0 such that this is equal to that. This is equal to that. Because can we do that? Of course, A0 is just a constant. And if we do this, then we got A0 is 0.529 Armstrong. This is what we call Bohr radius. And we usually measure everything in the atomic and molecular scale in Bohr radius. If you already use Quantum Espresso, for example, or VALS, the software Quantum Espresso, yeah, Rico, yeah, you use Bohr for measurement of length. But in Gaussian, you can use Armstrong already. But in the inside the calculation, inside the computer, it works in Bohr radius, not in Armstrong. So if you open the log file of the Gaussian output, you will see the internal coordinate and the change everything to Bohr radius. Using A0 is equal to 0.592 Armstrong, then this one or that one, if we multiply everything, we got 4.3597 times 10 to the power minus 18 joule. And this is the definition of 1 Hartree. This is the definition of 1 Hartree. Now, we use 1 Hartree as the unit now. With the Schrödinger equation for hydrogen atoms becomes like this, point number 8. Minus half, there is no mass anymore. There is no H bar anymore. And minus 1 over R ring. Remember, R ring in Armstrong, not R ring in Bohr radius, not Armstrong. Equal to this one. This is Hartree. This is Hartree. So you will find this equation. This is how Gaussian works using point number 8. So Gaussian will use Schrödinger equation using that formula, point 8. Dr. Mark, you can put it as the next question in quiz. We call it atomic unit. Okay. Now, using everything we have, energy of hydrogen atom is this one. 1 over 2 times 1 over n squared Hartree. If n is equal to 1, ground state, we got hydrogen atom energy minus, I also have minus here. Dr. Lucia, please make a note. Minus 0.5 Hartree. So if our calculation for hydrogen atom does not result in 0.5 Hartree, our software is wrong. So if you want to make a new code, new software to calculate atomic energy or molecular energy, you have to test it using hydrogen. If your software, if your code does not produce minus 0.5 R3 for hydrogen, your code is strong. And you must be surprised. You must be surprised if I told you long time ago, around 1990s, when people try to make DFT as a software like Gaussian, they cannot produce for hydrogen 0.5. Amazing, eh? They can calculate for many molecules, but not for hydrogen. Why? I will tell you maybe next week why they, in the first generation of DFT software, they cannot produce 0.5 R3. And since 1.6 times to the power 10 to the power of 19 joule is 1 EV, then we have this common knowledge, yeah? 1 R3 is equal to 27.211 electron volt. How do we get that? Easy. You can go to mathematical substitution, yeah? I will not explain further. All right. We almost there. Don't worry. I give you some minute to make a note before we go to the next slide. All right, now we will move to the next slide, which is the last section of this course. Important notes. Hydrogen atom, the most successful quantum theory. This is our topic. What the quantum theory predicted that make the quantum theory becomes the most successful for hydrogen atom. First, the quantum mechanics using quantum theory predict the size of hydrogen atom 1.5 Armstrong, which is correct. The Bohr radius also predicted by quantum mechanics 0.529, also correct according to experiment. Amazing. Hydrogen atom orbitals match with spectroscopy observation, the orbital SPDF and so on. Hydrogen energy minus 0.5 over n square R3 leads to the hydrogen spectral series like Lyman, Balmer, Passen, and so on. Also correct. And all of the match prediction come from the wrong approach because we only consider one body problem. That's the amazing point of how the quantum works. We use the wrong approach, but we got the correct answer. Why? So that's why I told you before, do not ask why. There is no philosophical reasoning behind this. It just works. All right. Why Mark Lee? I said it again, okay? Our topic today is hydrogen atom, the most successful quantum theory. Why it is successful? Because it predicts 4 things that come from scratch. First, the size of hydrogen, the Bohr radius, the atomic orbitals, SPDF, and also hydrogen energy. These 4, it comes pure from mathematics. We don't have any physical parameter inside the equation. What we call that? First principles. First principles. Schrödinger equation is first principle. We don't have any prejudice. We don't have any experimental value inside the equations. But the Schrödinger equation can produce these 4 physical quantities, which also exactly match with experimental values. And the most amazing, that make us scary, that make us amazed is all predictions come from the wrong approach. Why it is wrong? Because we use one body problem, which is not correct. hydrogen atom is two-body problem. Dr. Lucia, don't you feel wow?
Yes, Dr. Gaudian. It's
So
wow.
remember, this is quantum. Yeah, this is quantum mechanics. It works, but do not ask why it is work. Why it is work? You use wrong assumption. You use wrong approximation. In quantum, you don't need to answer this. Nah, ini bisa memberi inspirasi buat mahasiswa ITERA ya. Kalau ditanya orang tua kalian, kenapa kalian begini? Kenapa kalian begitu? Jawab apa? Saya ini quantum system, Ibu. Do not ask why. As long as it works. Nggak boleh begitu ya, salah ya. Mbak Nabila Sang terinspirasi pula dia. Jangan, nggak boleh gitu, Nabila. Again, I put it here to emphasize to you, quantum mechanics works, even though we don't know why it works. And I will go to the last slide for this today's session. Is the most important feature of hydrogen atom using quantum mechanics, which did not appear in Bohr's atom before quantum mechanics model. We have Bohr's atom, and Bohr's atom also produced a few of them. I will not go further. The most important feature of hydrogen atom using quantum mechanics, which did not appear in Bohr's atom, is the wave-like behavior of electrons in the form of orbitals. We need this feature to understand molecules, stability, and reactivity, including the resonance structure. Remember this. When we understand the result of Gaussian software, your calculations, if we want to understand the reactivity, the stability, we not only talk about the energy, also we talk about the NBO calculation, natural orbital natural bonding or orbital NBO. And using NBO, the basic of understanding NBO result is electron behaves like wave. What does it mean? If electron does not behave like wave, if electron behaves only like particle, you cannot split electron. You only have discrete electron. Electron either 1, 2, 3, 4, 5, and so on. But if it is wave, one electron can split itself half in this room using traditional chemist analogy, and another half in other room. And using NBO later on, NBO calculation, we will do it. We will see how one electron split itself. One part of this electron exists in this nucleus, and another part of it in other nucleus, and another part of it in another nucleus. It's so beautiful. And we cannot get it if we don't use quantum mechanics. And do not ask why one electron can exist at several places at the same time. Do not ask why. So if you want to be like that, I want to be in Lampung. At the same time, I also want to be in Makkah. You can do it by using quantum mechanics. Consider yourself as an electron. You can do it. We pray for you. Okay, I said it again. The most important feature of hydrogen atom using quantum mechanics, which did not appear in Bohr's atom, is the wave-like behavior of electrons in the form of orbital. Fitur paling penting atom hidrogen menggunakan mekanika kuantum yang fitur itu tidak muncul dalam model atom Bohr adalah perilaku elektron seperti gelombang dalam bentuk orbital. Nah, pemahaman ini, fitur ini kita butuhkan untuk memahami kestabilan dan reaktivitas molekul, termasuk menjelaskan struktur resonans seperti kasus ozon sebelumnya. Dua poin ini, these 2 points is a short introduction for you to analyze NBO results. The next question is, can we do the same approach using one body problem? Can we do the same approach to model helium atom? Can we consider one body problem for helium atom? The quick answer, no. We cannot use one body problem for helium. One body problem only valid for hydrogen. Unfortunately, there is no such thing besides hydrogen is hydrogen. Hydrogen is unique. You don't have any other system like hydrogen. So that's why when we talk about molecular physics, atomic physics, we do not consider hydrogen as an atom. Atom begins from helium, and then lithium, and so on. Why? Because hydrogen is, we can consider as one body problem, and the rest are many body problem. Helium, lithium, and so on are many body problems. So we cannot use one body problem to explain helium atoms. We need additional approach that leads to density functional theory, which is next week. Teaser, DFT is based on hydrogen atom. Wow, amazing, eh? I told you before that there is no such thing as hydrogen, but DFT still use hydrogen. DFT is based on hydrogen atom, another success story of quantum theory of hydrogen atom. That's all for today. But even though our course is not that much, but I already give you some introduction, analyze the Gaussian calculation from the your exercise. Like for example, you know already how Gaussian works. The Gaussian software use atomic system unit. It does not use joule and so on. Then you also know now that the orbital is the wave-like behavior of particle, and we need that to explain the reactivity and stability. And the wave-like the wave-like behavior of electron, we can study it using NBO calculations. Yeah, that's all for today. Next week we will begin our last lecture of theory, which is density functional theory. After that, we will focus on the hands-on. And before I give it to Dr. Mark, Dr. Lucia, and Dr. Vera, I also have an announcement that the group study will be announced by Dr. Lucia and Dr. Vera. Is it correct, Dr. Lucia? Yes, it is correct. You answered too long. All right, before we close it, perhaps Dr. Mark have some remark. Where is Dr. Mark? Oh, yes.
All right. Hello. Testing.
Iya, saya lupa.
Hello. Hello, can you hear me?
Yes, we can hear you.
Right, I can't hear myself. Hello, can you hear me?
Yes, we can hear you.
Okay. All right. So we have I wouldn't say a problem, but I think it also relates to what you have mentioned earlier, that the hydrogen atom is not, the DFT is not able to look at the hydrogen atom. So I think last week when we did the module, they were not able to look at the orbital of hydrogen atom. Is that one of the problem?
Yes, but please consider the selection of basis set, Dr. Mark. If you use higher basis set, you can get it. But if you use lower basis set, you cannot get it. It is correct.
All right.
Remember
you.
that the module, Dr. Mark, challenge student to find error. So it is correct that not all calculation will success. Some of them will lead to error, but error part of the study, so they can study it.
Okay, thank you.
Alhamdulillah. So some of question already answered. Dr. Lucia?
There is no question from students in
Really?
Dr. Dennis.
Dr. Vera?
Is there any question? No? Yeah, I think today is quite challenging for them because it's first time they know about the Schrodinger equations and the stuff.
Really? Oh, okay. Please help them, Dr. Vera. I will share the slide right away after I fix some grammatical errors.
Thank you.
And we have to announce the group, the working group, soon as possible, because we almost, even though we already begin module A1, A2, yeah, we already begin it, but still in the end, the formal agenda, the real agenda, we do it after the DFT, the theory of DFT.
Okay, Dr. Febrian.
So, Bilasang, apakah semua student sudah bisa akses Cyber Campus?
Not yet, Dr. Febrian, since from the UTM, I haven't received any further information from the department about the student ID.
Wow.
Yes, I haven't received any recent news.
Yeah, we need to talk about this behind the scene.
Yes.
We need to talk. We need either you or Ibnu go to the department ask the person again, person in charge. Yes.
Yes, I will, Dr. Febrian.
Thank you. Either way, we can still use manual without Cyber Campus. We put in Excel, for example, and share it with Dr. Mark. What about that, Dr. Lucia? For the group working group, yes. All right. And Dr. Mark, I don't really feel good today. I mean, I just returned from Lampung and I got sick, and I don't think I can continue until 1 p.m. So what do you think? What is the next agenda?
We can allow the students to continue with their work.
Yes. Yes. But I
And
cannot accompany you.
yes, no worries.
That's the problem. I need to sleep.
Sorry, Sorry, I have a problem with the speaker. There's a feedback. I can't hear myself if I switch it on. So they can't hear you. I can only speak to you and you listen to me, but they can't hear me. But they can't hear you. It's okay. It's okay. All right.
So if you don't mind, I will excuse myself. I need to take some medicine and take some sleep. But
Sure.
fortunately, our host today is Rizka-san. Thank you guys. Gabriel, terima kasih. Anissa, Naufal, terima kasih.
Okay.
Sania,
Yes.
alhamdulillah. Terima kasih Sania. Sabrina, who is Sabrina? Sabrina bukan dari Unair ya. Terima kasih sekali. Silakan kita pamit dulu ya. Sania, Anissa, Gabriel, dan Noval juga boleh pamit ikutan bersama saya. Terima kasih sekali lagi. Thank you very
Sorry,
much, guys. Next week we will. Yes, Dr.
sorry.
Lucia.
Do we need to take picture?
picture.
Yes, picture. Gabriel, Anissa, Noval, tolong nyalakan dulu kameranya. Sania.
Oke, baik. Satu, dua, tiga. Sekali lagi. Satu, dua, tiga. Sudah, Pak.
Alright. Thank you guys. Subhanakallahumma wa bihamdika. Asyhadu an la ilaha illa anta. Astaghfiruka wa atubu ilaik. Alhamdulillahirabbil alamin. Assalamualaikum warahmatullahi wabarakatuh.